Alright guys, so in this video, mm, what I'm going to show is I'm going to solve two questions which I already solved during the live session, but for some reason due to technical issues I couldn't record that session. So I am resolving it again so that in this video, so that whoever haven't attended, then it might be helpful for them. So that's the reason I'm actually re-recording, resolving this two questions. Basically, it is based on nuclear rockets. Okay, so let's quickly get into the question. Let's solve it. And if you have any questions, you can either post it in the discussion forum, or you can come back the next class and you can ask me that question. Okay. All right. Um, so the topic of this today's presentation is nuclear rockets. Okay, so we are going to solve two questions in nuclear rockets. Both are basically nuclear thermal rockets. One is fairly easy, one is little bit involved. You need to understand certain physical concepts. Okay, so the first question deals with um, a nuclear rocket in which hydrogen gas is heated. Okay, the we all know what is nuclear thermal rocket is. The basically it's a thermal rocket, which means you have a high temperature gas which is going to expand in the nozzle. But the way we get the high temperature gas is different. So usually we do combustion in a solid propellant or liquid propellant, engines. Here the energy, the gases are heated up by the nuclear reactor basically. Okay, so nuclear reactor, nuclear energy is actually converted to thermal energy, which is then converted to kinetic energy in the nozzle. Okay, so that is the main idea of this nuclear rocket. The hydrogen gas is heated in a nuclear thermal rocket in a particle bed fission reactor. Okay, so this is the particle bed uh, reactor. The particles here are basically the nuclear pellets basically. Okay, the uranium, enriched uranium or plutonium, whatever the nuclear isotope is, that is the particle that is taken as a particle, as a pellet. And uh, it that's been arranged as a fission reactor. Okay, the heat generated in the fission reactor at a critical equilibrium condition is 2 megawatts. So the total heat generated by this nuclear reactor is 2 megawatts. This nuclear energy is converted to kinetic energy of a jet that exhausts the nozzle with a velocity of 4,000 meters per second. So whatever the nuclear energy we supply, which is a form of heat energy, is then converted into kinetic energy in the nozzle, and the jet velocity, final jet velocity we reach is 4,000 meters per second. Okay, determine the following parameters for the nuclear thermal rocket. So we were asked to find certain parameters. The parameters are specific impulse. First we need to find the specific impulse. What is the mass flow rate through the nozzle? That's the second question. Assuming that entire energy due to chemical reaction, here in this case it's a nuclear reaction, is converted to kinetic energy of the jet. So whatever the heat you supply is going to get converted to kinetic energy. That is what we were asked to assume. And if you assume that, what would be the mass flow rate through the nozzle is what we are asking. Okay, and then the third is thrust developed by the rocket. So let me quickly write down the given uh, data. So we have q dot generated, which is around 2 megawatts, and we have jet velocity is 4,000 meters per second. Okay, these are the two important things given, and we need to first find out what is the specific impulse of this rocket. Okay, the specific impulse here is we, of course, we all know a lot of formulas to find out the specific impulse, but the here this specific impulse is actually directly going to be the jet velocity of the uh, nozzle, or the jet velocity of the gases exiting the nozzle. The reason is usually the ISP is defined as F by m dot, and we know the thrust is going to be m dot into Vj, right? M dot into Vj, plus there is going to be some pressure thrust. Okay, some pressure thrust. Let's say P, or let me write it out like that, F times P, which is going to be a function of what is the P exit pressure at the exit and what is the ambient pressure. Based on that, there will be a pressure thrust like acting on the nozzle, exit pane of the nozzle, and that is also going to improve your thrust or decrease your thrust based on the operating condition you are in, and that divided by the total mass flow rate is actually your specific impulse, right? And um, here in this question we have not been given that anything about the pressure thrust. We have not been given what is the exit pressure, what is the ambient pressure, so it's actually not relevant, and we can also take that we can just ignore this. Okay, we can ignore this, and if we do that, then we will end up having m dot vj by m dot, which is going to be simply vj, which is the jet velocity. So ISP here is actually jet velocity, which is 4000 meters per second. Okay, so this is fairly simple. Now the second question is, what is the mass flow rate through the nozzle? M dot through the nozzle is the question. So to find m dot, what is the other information given was, assuming entire energy due to chemical reaction is converted to kinetic energy. So we may need to use this information in order to get the mass flow rate. So how do we use this information? So we know, what are we telling? We know that whatever the heat generator is going to get converted to the kinetic energy of the nozzle. And we know here the heat generated is in watts, which means it's in power, the rate of change of energy. So then here also this actually it's going to be Q dot generation is equal to d by dt of kinetic energy. Kinetic energy of the gases. And we all know the kinetic energy of the gases, it is nothing but half m dot half m vj square. This is the kinetic energy of the gas. Now since vj's are same, we can take that out, and dm by dt is what the m dot is, so we can directly write this as q dot generation is equal to half m dot vj square, and we need m dot, so m dot is nothing but 2q by vj square. Okay, and this is going to be equal to 2 q dot generation. So 2 into q dot generation is 2 megawatts, so 2 into 10 power 6 watts divided by vj is 4000 seconds, sorry, meters per second, 4000 meters per second, and square of that. So if we calculate the m dot over here, it's going to be 2 into 4 into 10 power 6 divided by 4000. So it's going to be around 0.25 kgs per second. Okay, this is the m dot through the nozzle. Okay, this is how we find out. So basically what we did is we did energy conservation. Whatever the energy given to the given by the what do you call, the nuclear reactor, is actually used for converting it to kinetic energy in the nozzle. Okay, this is nothing but an energy conservation. In addition, we are telling that there is no heat loss to the surroundings, there is no irreversibility, all those things we assume. That's how we were able to get this m dot. Okay, so you may need to notice what are the uh, physical concepts we are using here, because that is what is going to be helpful when you are solving your problems. Okay, so we cannot blindly apply some formula, and we should not blindly apply certain formulas. Okay, and the third question here is, what is the thrust developed by the rocket? So this we all know, the thrust developed by the rocket, which is nothing but F is equal to m dot into Vj plus the pressure thrust, but we are going to just ignore it. Okay, because it's not been given in the question. And since we know m dot, it's going to be 0.25 into Vj is 4000, which is will be equal to 1000 newtons. Okay, yeah. So this is a fairly simple problem, which is just deals with energy conservation, and how to find some performance parameters like thrust and specific impulse of a nuclear thermal rocket. Okay. Now, the second question is about the same nuclear thermal rocket, but it is in a cycle. So basically, we are going to analyze, uh, how the propellant is moving from tank to the reactor to the nozzle. We are going to analyze it as a separate cycle. Okay, and so so to save time, actually, I already draw the schematic, but let's read the question once again uh, for the sake of completeness. Okay, a nuclear thermal rocket operating in a hot gas breach cycle generates a thrust of 800 kilonewton. Okay. In this rocket, the liquid hydrogen is stored in tanks at a temperature of 20 Kelvin and the pressure is zero point 0.2 megapascal. So basically, there is a liquid hydrogen tank, and the hydrogen stored is actually 20 Kelvin and zero point 0.2 megapascal is the pressure in the liquid hydrogen tank. Okay, and now from the tank, the hydrogen gas is actually liquid at this state. It is pumped using a turbo pump. Okay, to a higher pressure of 8 megapascal. So using pump, we are increasing the pressure from zero point 0.2 megapascal to 8 megapascal. Now the high pressure liquid hydrogen from the pump is supplied to a coolant channel. So now after it got pumped from zero point 0.2 megapascal to 8 megapascal, it has been supplied to the coolant channels of the reactor. So that's what been said here. The high pressure is supplied to the coolant channels surrounding the nuclear reactor. Okay, so what happens is, in a nuclear reactor, we know that the temperatures are going to be very high, and we need to safeguard our nuclear reactor. If not, it leads to a nuclear meltdown. So we send certain amount of hydrogen, or the whole of hydrogen gas, which is at a cold state at this state. So after the pressure, after it comes out of the pump, it will have some temperature which is going to be fairly less. So it's going to be, it centers at 20 Kelvin, so it will be little higher than 20 Kelvin. And since 20 Kelvin is a low value, you can use it to cool down the reactor. Okay, using a heat exchanger, basically through a heat exchanger. So that's what I have drawn like this. So it goes like this, and it actually goes through the reactor, gets cooled down, and then it comes out. Okay, so uh, just for a schematic I have drawn like this, but it goes through and cools down this whole orange mesh reactor. Okay, this is a nuclear reactor. Now once it cools down and when it comes out, it is going to be at 400 Kelvin. So that is, so they say the temperature of hydrogen at the outlet of coolant channel is 400 Kelvin. Now the temperature of hydrogen at the reactor exit is 4000 Kelvin. So whatever it came out of coolant channel is actually fed into reactor, and when it comes out of the reactor, it is 4000 Kelvin. Okay, and it doesn't stop there. The warm hydrogen from the exit of coolant channel is mixed with hot hydrogen gas bled from the reactor exit in the ratio of 5:1 and is used to drive the turbine. So what they did was, whatever the warm hydrogen came and whatever the reactor gas came, we took some portion of it, we took it and we mixed it together. Okay, we mixed with warm hydrogen gas and the hot uh, you know hydrogen gas from the reactor exit, and we mixed it together with a certain ratio of 5:1. Okay, and after mixing, what are we doing? That is used to drive the turbine. So that is given as a input to the turbine. Okay, so that's what I have done. So some are going in this way, some are going this way, and then they are mixing here, and then they are going to the turbine. And after turbine, it goes through the turbine, it gets expanded, and it comes out as a at 350 Kelvin. Okay, the temperature of gas at the exit of the nozzle of the nuclear reactor is 250 Kelvin. That is also given. So whatever the exit of the nozzle is 250 Kelvin, and the turbine outlet temperature is 350 Kelvin, as I said before. Okay, and then we have certain properties of hydrogen gas. Hydrogen gas specific heat is 14.5. We were asked to assume that it is same at all the temperatures. So whatever the temperature we are going to encounter, we are going to use the Cp to be same as 14.5 kilojoules per kg Kelvin. Okay, and the density of liquid hydrogen is also given, which is 71 kgs per meter cube. Okay, so given this is the question, given this is a problem statement, what are the questions they are raising is, Determine the specific impulse of this nuclear rocket, neglecting the contribution from turbine exhaust and no dissociation of hydrogen. So we were asked to find the specific impulse, but with certain assumptions. Let's not take the outlet of the turbine into contribution of specific impulse. So that is also we are going to ignore. And whatever coming out, you can see that it's going to be at 4000 Kelvin. It's fairly hot hydrogen gas. Now, if you have a high temperature hydrogen gas, then there is it's most likely that it can dissociate into hydrogen atoms. Okay, and this dissociation, because of this dissociation, we are actually losing some of the performance in terms of ISP. Okay, and what we were asked to you know neglect is, let's assume that there is no diffusion for hydrogen gas. Okay, so that is one of the assumption we are going to take. And if you take those assumption, what would be the ISP? It's what they are asking. And the other things are, the second question is mass flow rate of hydrogen to the reactor. So what is the mass flow rate coming to the reactor is the question. Okay, and what is the if the efficiency of turbine and efficiency of pump is this much and this much, which is zero point 0.8 and 0.2, determine the fraction of total mass flow rate of hydrogen through the turbine. So basically, they have the efficiency of pump, efficiency of turbine, and if this is the efficiencies, then I wanted to know what is the amount of mass flow rate through the turbine, or what is the fraction of mass flow rate through the turbine. Fraction in the sense, what is the in the total mass flow rate? What is the amount of mass flow rate is going through the turbine? uh, okay, which is not going to go through the reactor, and because of which we are going to lose some uh, performance which we would have got if we redirect that mass flow rate to the rocket. Okay, so that's why that you know parameter has been asked here. And the final question is, what is really the mass flow rate through the turbine of the hydrogen? Okay, so we were also asked to find the fraction. We were also asked to find the mass flow rate of the hydrogen. Okay, so I hope the question should be, question is fairly long to understand, but it is easy to understand. Okay, so now um, this is the schematic. We have hydrogen, which is at 20 Kelvin and zero point 0.2 megapascal. It's going through the pump. It raises temperature to 8 megapascal. Okay, and then it goes through the coolant channel, gets heated up to 400 Kelvin, and whatever you know uh, the reactor exit gas coming out is actually mixed with this 400 Kelvin, and then is given to the turbine at certain temperature, which we don't know. We have to find out. And from there, turbine the exit temperature of turbine is 350 Kelvin, and the exit temperature of the nozzle is 250 Kelvin, and the combustion chamber temperature, or the temperature of the gas at the exit of the nuclear reactor, is 4000 Kelvin. Okay, so these are the inputs. In addition, there are few more inputs given. Let me quickly address those also. So I guess thrust is given. The thrust of this nuclear reactor is nothing but 800 kilonewtons. And uh, what are the other important parameters? The efficiencies are given. Efficiency of turbine is 0.8, and efficiency of pump is 0.7. All right, and CPs are given. Density of liquid hydrogen. Density of liquid hydrogen is 71 kgs per meter cube, and the CP of hydrogen is 14.5 into 10 power 3 joules per kg. All right, I hope these are the important parameters, given parameters. Now first question is, we need to find the specific impulse. Okay, specific impulse. So to find the specific impulse, we can use the same formula. Basically, the uh, specific impulse here, it is going to be, ISP is going to be same, F by m dot, you can say, but the thrust is going to be m dot into Vj, Again, we will neglect the exit pressure and ambient pressure because it's not given in the question. So basically, this is nothing but jet velocity, right? Now, if I want to find the jet velocity for this configuration, how do I find the jet velocity? So we all know the formulas. So this is what we usually remember. The jet velocity is nothing but 2 gamma by gamma minus 1 r naught Tc by molecular weight, and then you have 1 minus Pe by Pc or Pc by Pe, I'm not really sure. So this is the jet velocity equation we all know. This is what we used to solve, but the problem is we do not have the pressures, right? Or we may need to find the pressures. And uh, so even if you find the pressure, or you actually have temperature, you actually have the temperature of the exit and temperature of the combustion chamber. So basically you can find this term, and you need to find gamma of the hydrogen gas, you need to find molecular weight of the hydrogen gas, which we know, and the temperature of the chamber is already given to be 4000 Kelvin. So basically we can use this relation, I mean we can use these inputs and you can find the jet velocity. Or the easiest way is, how did we arrive at this equation, right? That is one of the question you should ask. How did we arrive at this equation? We actually did what do you call the energy conservation, basically, right? Whatever the m dot with which it comes in. So basically, if you remember in your fluid dynamics, maybe you will remember it as a steady flow energy equation, okay? And the so let's say if I want to write it as a steady flow energy equation, it's going to be at the inlet, it's going to be m dot into h1, or at the chamber it's going to be m dot into hc plus vc square by 2. But at the chamber velocity is almost zero, so we can write whatever the energy, it's actually thermal energy, which will get converted into kinetic energy. But here there will be an exit enthalpy plus vj square by 2. So this is basically your steady flow energy equation, if you remember from your fluid dynamics, or even we have addressed this here. So basically the kinetic energy gain by the gases while it is flowing through the nozzle is basically equal to the change in enthalpy of the gases, right? So that is the energy conservation principle we apply. So let's say if we do this, then we will end up having, we can cancel this mass flow rates, and we will end up having Vj is equal to 2 times into Hc minus He, or delta H, you can say, square root of that. Okay, and what we know is, we know H is nothing but Cpt, at least at this point of time, in within the scope of this problem. It's going to be simply Cpt, so it's going to be Cp times Tc minus Te. Remember, we have assume that Cp is same for all temperatures, so that's how I was able to take the Cp out. All right, so now let's try to substitute all the values here. Cp is nothing but 14.5 into 10 power 3, and the chamber temperature is 4000 kelvins, and the exit temperature is 250 kelvins. These are given in the question. So now let's if you solve this, what would happen? So you have 4000 minus 250 into 14.5 into 10 power 3 into 2 square root of this. Alright. So the jet velocity I get upon solving this is 10,428.3 meters per second. This is the jet velocity I get. Okay. Which is actually equal to ISP. ISP is also 10,428.3 meters per second. Okay, which is what we were asked to find out. All right, so ISP we obtained. So basically from the jet velocity relation. Now the second question is about what is the mass flow rate of hydrogen in the in kilograms per second through the reactor. That is the question. So what would be the mass flow rate of hydrogen in kg per second through the reactor? Which is, so basically we were asked to find what is the mass flow rate through the reactor? Is what we were asked to find. Okay, which is going to contribute to the thrust basically. Okay, what is the mass flow rate through the reactor which is going to contribute to the thrust basically? And this mass flow rate is not the total mass flow rate, which we all agree, because some of the mass flow rate is taken for the turbine also, right? Some of the mass flow rate is taken for the turbine, and whatever the turbine outlet is, we are actually going to ignore that. So, but there is some mass flow rate we are going to take it to the turbine. So that will not be the mass flow rate through the reactor will not be same as total mass flow rate. Okay. On that note, let's try to find out mass flow rate through the reactor. Okay. So the mass flow rate through the reactor is going to be basically um, what it is going to basically contribute to the thrust, right? And what we know is we already know the thrust. Thrust is given as 800 kilonewtons, switch into 10 power 3 newtons. And what we know about thrust is going to be m dot into Vj. We do not have a pressure thrust here. So we already know Vj, so we know F, so we can directly find the m dot. M dot is m dot through the reactor. Okay, reactor. Maybe I will, for the sake of completeness, I will write. Now m dot reactor is nothing but F by Vj, which is 800 into 10 power 3 newtons divided by 4000 meters per second. So m dot through the reactor is going to be uh, around 200 kilograms per second. Okay, so I'm sorry. So VJ is actually okay. I think I took the old questions VJ. So basically VJ is nothing but 10428.3 meters per second. Sorry about that. This VJ we need to take here. This is what we found out. Okay, so if you calculate that one, it's 800 into 10 power 3 divided by 10428.3. So which is coming out to be 76.71 kgs per second. This is the mass flow rate through the reactor. Okay, this is which is what contributing to the thrust. Okay. All right. Now let's try to find out what was the third question. Third question is to, if the efficiency of turbine is 0.8 and the efficiency of pump is 0.7, determine the fraction of total mass flow rate of the hydrogen through the turbine is what the question is. So basically we were asked to find m dot of turbine by m dot of what was the total. Okay, this is what we need to find out. How do we find out this part? So what would be the concept behind finding this is the question. Now what also is given in the question is we were asked to use an efficiency, so we may need to use these efficiencies. Efficiency of turbine and efficiency of pump is given. So so the turbine pump combination is because you want to drive a pump, and the power is given by the turbine. Okay, so basically whatever the power generated by the turbine is going to be equal to the power uh, used by the pump. Okay, so let's try to equate those two things, and let's try to find out whether it is leading to somewhere else. Okay, so the power of pump, how do we calculate? Is basically we have to multiply the volume flow rate through the pump, right? And the pressure difference across the pump. And the pressure difference across the pump is, we know, either grad P or you know delta P. So let's write it delta P. The pressure difference across the pump is nothing but 8 megapascal minus 0.2 megapascal, which is going to be 7.8 megapascal. This is the pressure difference across the pump, and the mass flow rate and the volume flow rate to the pump, you can write it in terms of mass flow rate. And we should note that the mass flow rate by if the pump is going to act on the liquid hydrogen. So hydrogen is still in liquid state. That's why we need to divide it by the density of liquid hydrogen. Now, what is this mass flow rate? This mass flow rate is going to be the total mass flow rate going through the pump. Okay, so then this mass flow rate is nothing but, let's write it down, it's nothing but its total mass flow rate. Okay, let's put these two things together. This would become m dot total divided by rho of LH2 into gradient of or difference pressure difference of pump. And another important thing is, since this pump has an efficiency of pump is 70%, I guess. Is it 70%? Yeah, efficiency of pump is 70%. So this might be the ideal um, pump power you may need to give, but since the efficiency is just 70%, you may need to give extra power, so you need to divide it by the efficiency of pump. Okay, this is the overall power of the pump. You need to divide it by the efficiency of pump. Okay, so now let's look at the turbine side. This is about pump. Now let's look at turbine. How do we find the power of the turbine? So in the turbine, you can see that the work is coming out. So let's say if I want to separately draw this, um, so turbine would look something like this. Okay, this is the turbine, and so something is coming in at certain temperature and something is going out at certain temperature, which is 350 Kelvin, we all know. And the mass flow rate to the turbine is going to be m dot turbine. It's not the total mass flow rate. Not all the mass flow rate is going through the uh, the turbine, because most of them are going through the reactor and it is getting expanded in the nozzle, and which is what is creating thrust. So only some fraction of mass flow rate of the total mass flow rate is going into the turbine. Let's call this m dot turbine. Okay, this is the m dot turbine. Now what also happens from the turbine is there is going to be work output, work done by the turbine. So basically this work done by the turbine is nothing but m dot of the turbine into the change in enthalpy across the turbine. Okay, and the change in enthalpy here is going to be simply Cp times T in minus 350. Okay, that is what we write as a power of the turbine. Let's directly write uh, the relation. So it's going to be m dot of turbine into delta H, which is equal to m dot of turbine into Cp times T in minus 3. Okay, this is the power of turbine, but it is if it is an ideal. So this also has an efficiency of how much, 80%. So it is going to give us only that much. So you should multiply it by turbine efficiency. Here also you should multiply by turbine efficiency. Okay, now we all know that the power of pump is actually coming from the turbine. So if we equate these two, let's try to equate these two. What happens? M dot total delta P of pump divided by rho of LH2 into eta of pump is equal to m dot turbine into Cp of T in minus 350 into eta of turbine. Okay, this is the relation. So this is the relation. So for what we are interested in, if you go back, we are interested in getting this m dot turbine by m dot total. So if I rewrite this in terms of that, m dot turbine by m dot total is equal to, uh, let's take all the other things on the other side. So you will have delta P of pump divided by rho LH2 into eta of pump, and in division you will have 1 divided by Cp times T in minus 350 into eta of turbine. Okay, this is what you will have. And now so we know what is delta P of pump, we know density, we know eta, we know Cp, we know eta of turbine, but we still don't know the temperature which is with which the uh, gas is entering the turbine, which we need to find out. Okay, so for that we may need to use certain clues given in the question, which is what is the temperature. So what has been given? The warm hydrogen from the exit. The warm hydrogen from the exit of the coolant channel is mixed with total hot hydrogen gas. Okay, so this coolant channel is giving at 400 Kelvin, which is warm, and then the hydrogen, the reactor exit is giving hot hydrogen gas, which is at 4000 Kelvin. These two are getting mixed, and then send it to the turbine. So which means, like, the mixing, what are the temperatures before mixing. You just need to find what is the temperature after mixing. That is the idea. So if I want to draw it separately, you have one stream of hydrogen coming, which is coming from coolant channels. Okay, let's call this m dot as m dot coolant channel m dot cc. And what is the temperature here? We have 400 Kelvin. Okay, now there is another stream coming from the reactor exit, which is at 4000 Kelvin. Now at a certain proportion we are just mixing, so that proportion is actually taken care by m dot. So let's call this as m dot into reactor exit Re. Okay, so there is some m dot of Re is coming, m dot of Cc is coming, and what we are doing is we are mixing these two. Okay, so I'm just drawing this as a lines. So I'm mixing these two, and what I'm getting is I'm getting m dot turbine. So this is the mass flow rate with which the gases get into the turbine, and the temperature is some T. So this is what we have. So using this information, what we can do is we can actually do energy balance. So the energy entering and energy leaving should be equal to should be same, right? That is the energy conservation. All these are steady flow analysis. So again, you can use steady flow energy equation to develop to do this analysis. So basically what I'm trying to say is m dot into cc times hcc is the energy with which the gas stream is entering, which plus m dot into re into h into re is the energy from the hot hydrogen gas is entering, which should be equal to m dot into turbine into h into turbine. Okay, now we know it's a h, we can write it as cp into t. So let's write that down also. mcc is equal to cp into tcc. tcc is nothing but 400 Kelvin plus m dot re into cp into t re, which is nothing but 4000 Kelvin, which is equal to m dot turbine cp into t of turbine inlet actually, h turbine inlet, so which is T in, that's what we refer it as. And we know cp is we are going to take it to be constant. So if it is not, you cannot ignore it. Okay, please keep that in mind. And if this is the case, then let's try to now what you can do is you can actually, if we are interested in T in, so let's write T in. T in is nothing but m dot cc, that's divided by the turbine, m dot turbine into tcc plus m dot re divided by m dot turbine T. Okay, now what we know this is going to be 5:1 ratio. 5:1 ratio. What is the 5:1 ratio? So m dot cc by m dot re is equal to 5/1. That is what we know. And what is m dot turbine then? So m dot turbine is going to be some, let's say, you call it, so let's say we call it m dot turbine is equal to some x. Okay. Now, this 5:1 is nothing but m dot cc is equal to 5 times m dot of re. Okay, and m dot turbine is nothing but m dot cc plus m dot re, which is nothing but is equal to 6, right? 5 m dot re, 6 times m dot re. So now we can write this x as, or we can write m dot re by m dot turbine is equal to some x by 6. Okay, so this x can be anything. It can be, so for now we can take it, let's say we'll consider it's for a 1 kg per second. If you consider that, then 1/6 of it is coming from the uh, what do you call the 1/6 of it is coming from the reactor exit, and 5/6 is coming from the m dot c. Okay, so here, so this m dot turbine is still unknown, so basically we took the x to be on the other side, so this is going to give you 1/6. Okay, so let me write it down again. So this is giving us m dot turbine is equal to 6 times m dot re, and in the equation we have m dot re by m dot turbine. Okay, which means m dot re by m dot turbine is equal to 1/6. Now if m dot re by m dot turbine is 1/6, then similarly you can write this as m dot cc also you can write. M dot cc is nothing but 5 times m dot re, which is nothing but 1/6 times m dot turbine. Basically I could have just simply used this ratio and write 5/6 and 1/6, but I just want to show you how this comes. M dot cc by m dot turbine is equal to 5/6. So we just substituted there, so which gives us T in is equal to 5/6 TCC plus 1/6 TRE. Alright, so if this is the case, we know TCC and TRE, this is going to be 400 Kelvin and 1/6 into 4000 Kelvin. So which is actually going to give us, how much is it going to give us? 5 into 400 by 6 is 333 plus 4000 by 6 is actually 1000 kelvins. So this is the inlet temperature to the turbine. Okay, and what we used is we used energy conservation, which you should note. So basically we have been using energy conservation everywhere, which is what I want to stress here. It's not some random formula, it's basically energy conservation. So you just need to know in fluid mechanics or in rocket propulsion, in thermodynamics, everywhere. There are only few principles you need to remember. One is mass conservation, energy conservation, and then you also have momentum conservation in terms of fluid mechanics, right? So only these three principles is actually enough to solve most of the problems you will face. Okay. So yeah, so we used energy conservation to find the T in. So once, since we know T in, we can directly plug in this formula to find m dot turbine by m dot total. Okay, let's put it in. Let me copy it from here. Copy, paste. All right. So here the delta P we all know it's 7.8. 7.8 into 10 power 6 megapascals divided by density is 71 kg per meter cube and heat of pump is 0.7 multiplied by 1 divided by Cp is 14.5 into 10 power 3 and T in is 1000 Kelvin we just found out minus 350 Kelvin and efficiency of turbine is 0.8. Okay. Now if you find out what is the uh, m dot what is the fraction, it's going to be 7.8 into 10 power 6 divided by 71, sorry, 71 divided by 0.7 divided by 14.5 divided by 10 power 3 divided by 650 divided by 0.8. Okay, so this is coming out to be 0.021. Okay, this is the ratio. This is the ratio of mass flow rate through the turbine to the total mass flow rate. So you can see it's just 2.1% of the total mass flow rate. So let's write that down. Mass flow rate of turbine is nothing but 0.021 times the mass flow rate of the total. All right. So this is how you find the mass flow rate. I mean, this is one of the way to find the mass flow rate, which is done. Now, what is the mass flow rate of hydrogen in kg per second through the turbine? Okay, what is the mass flow rate of hydrogen in kg per second through the turbine? So we found the fraction. Now we need to find the actual mass flow rate. So to do that, let's let's collect all the information we had till now. The m dot turbine is equal to 0.021 times m dot total, and what we know is m dot total is equal to m dot reactor through the reactor. What are the m dot going through the reactor which is contributing to the thrust we have, plus m dot of turbine. Okay, these two we know. And what we know of the m dot of reactor? M dot of reactor is we already found it is going to be 76.71 kgs per second. Now we need to use all three information. So we have three equation and three unknowns, or basically this is not considered as a unknown. So we have two equations for reactor. We know mass flow rate of turbine and total mass flow rate is what we need. So we have two equation and two unknowns. You can solve and you can I mean not solve, you can substitute and you can find the solution. Okay, so let me go ahead and do that also. So let's take this m dot of total is equal to 76.71 plus m dot of turbine. And what is m dot of turbine? Let's substitute it here. So m dot total is equal to 76.71 plus 0.021 m dot of total. Okay, now if I take this on this side, m dot of total minus 0.021 m dot of total is equal to 76.71. So I can write this m dot of total into 1 minus 0.021 equal to 76.71, and this is going to give me m dot of total to be 76.71 divided by 1 minus 0.021. Okay, how much is that? 1 minus 0.021. 76.71 divided by answer. So the total mass flow rate is 78.355 kgs per second. And what we also need to find out, we need to find out m dot of turbine. M dot of turbine is nothing but 0.021 times the total mass flow rate, which is 78.355, which is going to be equal to 1.645 kgs per second. This is the final answer. Okay, so this is the total mass flow rate through the turbine, which we can obtain by simply manipulating these two equations. But nonetheless, this is a little bit challenging because it puts it actually questions a lot of fundamental things. So basically, you you might end up solving this question without even knowing the fundamental concepts. So basically, we did energy conservation at each and every step. We did energy conservation across the turbine. We need energy conservation for the mixing. We did energy conservation in the nozzle. So uh, these things you may not know, but you might just use the formulas to get it. But it's always better to revisit the fundamentals and understand things. Okay, and that is why I actually picked this question. This is actually a solved question from the rocket propulsion book by Professor K. Ramamurthy. You're free to look into it. Okay. Um, yes, that's it. So we solved two nuclear thermal rocket problems today, and that I hope that would be helpful for you to solve the week 12 you know assignment problems. Okay, on that note, I will end this session today, and we'll meet once or twice to for revision. Okay, so there is going to be a revision session on 18th of April. I think that is what my preferred slot for the revision as per NPTEL. uh, I hope you will be getting the links soon. And since some students have been asking that they may not be available on the weekdays, so I will be doing one more revision session on 20th of April, Saturday, same timing from 7 to 9. Okay, and yeah, so you can attend either of them, or you can. I will be uploading the recorded videos also. You can watch them. I hope that should be helpful for you. All right. With that note, I will close this session. Sorry, I couldn't manage to record the session, so so that's why I read it for problem. All right. Thanks for watching. We'll meet next session. We'll meet in next section.